Hello everyone and welcome to my channel. Myself Dr. Kurrabalu. I am working as a assistant professor in the Department of Electrical Engineering at NIT Calicut. Currently, I am teaching microprocessor and microcontroller subject to second year third semester BTech students at NIT Calicut. Today, I am starting the number systems. If you don't understand number systems properly, you will face many difficulties in understanding and learning microcontrollers and microprocessor subject. Why? Because everything inside the microprocessor and microcontroller is based on the number system concept, starting from the memory address to the instruction codes. So before we dive into programming of microprocessor and microcontroller, we must master this foundation of number systems. Like number systems are heart and brain of microcontrollers and microprocessors, just like heart pumps blood and brain process information in our body is reflected to the number systems. Like number systems supply data and process instruction in digital systems. Without understanding them, you can't truly understand how any microcontroller and microprocessor works. In this session, I will teach how to work with different number systems like decimal, binary, octal and hexadecimal, and how to convert one number system to other number systems and vice versa. By end of this session, you will not only understand the theory but also be able to solve problems quickly, which will help you in both exams and interviews. Now we will start the basic definition of number systems. So what is number system? Number system is a way to represent numerical values using the set of symbols or digits in digital circuits. Since digital circuits work with binary signals, only two states, that is 0 and 1. 1 indicate on or high and 0 indicate off and low. Different number systems are used to represent data representation, storage and processing. In digital circuits and systems, the most commonly used number systems are binary number system, octal number system, decimal number system, and hexadecimal number systems. Now we will discuss one by one. First, start with the binary number systems. The binary number system, it has a base or radix of 2 and it possesses the two different symbols, that is 0 and 1. It is a method of representing the information using only two binary digits where each bit is a fundamental unit of data. It is the most fundamental number system in digital circuits and computer systems, as all operations are based on binary logic using two states such as 1 and 0. And the next number system is the octal number system. It has the base or radix of 8 and it possesses the 8 symbols, that is 0 to 7. It is a method of grouping binary numbers in sets of 3 bits. Okay, here the each bit has a each digit has a 3 bits. So binary, if I represent 0 in the octal system, it is 0 0. If I represent the 1, it has a 3 bits, making long binary sequence easier to manage. It is a very important in digital computer system because octal number system simplifies the task of entering, reading, and interpreting the binary data, saving both time and effort. And the next number system is the decimal number system. It is a base or radix of 10 and it possesses the 10 different symbols, that is 0 to 9. But in the later slides, I will show that the decimal number system, it doesn't have the conversion tables. Okay, we will discuss in the later. Now it is a method of representing numbers using the powers of 10 and is used mainly in user interface and human centric outputs. Actually this number system is came because of the human fingers. So human fingers has the 10. We can easily communicate to the other person with the 10 fingers. Okay, 1 2 3 up to 10. It is started from the in the binary or in the a number system, it is start from the 0 to 9. Total 10 symbols we can represent with the 10 fingers. It is the most commonly used number system in daily life because it is easy for the human to understand and perform the arithmetic logic systems, logic calculations. And the last system and the most important system in the number system is hexadecimal number system. See, our entire microprocessor and microcontroller will based on the hexadecimal number systems. And the later class, in the later slides, I will show that the assembly language and the high level language. like high level language and assembly language and machine language. The machine language will work on zeros and one, and the assembly language will mainly focus on the hexadecimal number system, because in the assembly language we will have the mnemonics or opcode. The each opcode is represented in terms of the hexadecimal number systems. Okay, you will miss here the hexadecimal concept, then you will face the many problems in understanding the mnemonics or opcodes of the instruction set of the any particular PIC microcontrollers. So here it has a base or radix of 16 and it possesses the 16 different symbols. Okay, 0 to 9 and A to F. So this number system is also called the alphanumeric number system, because it has the numerical value 0 to 9 and it has the alphabetic value A to F. So this system is called the alphanumeric system. Why different number systems is there in the digital systems? The binary number system is the fundamental to digital circuit design, as logic operation and data storage are implemented using the bistable elements that operate in the two states, such as zeros and ones. It is referred as the native language of computers. Like that, if I go to the Telangana, my native language is Telugu. If I am working in the Kerala is the native language is the Malayalam. If I go to the any other states, Delhi and the other side, in their native language is the Hindi. Like that. If I go to the Tamil Nadu, nearer to the Kerala, their native language is the Tamil. And if I go to the Karnataka, the native language is the Kannada. Like that, different native language is there. So here, the native language of the computers is the binary, that is represented the zeros and one, and the octal and hexadecimal number. Octal and hexadecimal number, we will see that represent enough 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. Okay, 2 to the power of 0 is the 1 bit, and the 2 to the power of 1 is the 2 bits, and the 2 to the power of 3 8 bits. Like that, we have to see that whether in the decimal number system it is applicable to represent the 2 to the power in terms of the 2 to the power, because the native language of the computer or the binary computer is a binary number system. So anything we have to represent in terms of the base base is the 2, and the anything you can change power 0 1 2 3 4, then you map in the binary number system. So here binary number system, octal and hexadecimal system is much more convenient to represent the data in the computers and microprocessor and microcontroller. The decimal number system is the human interaction, because it has to convey the other person in terms of the numerical values, because the each person has the 10 fingers, then easily we can convert the 1 2 3 like with the 10 fingers. And why do computers operate on binary number system instead of decimal number systems? So computers operate on binary number system because their fundamental building blocks, such as the transistors and logic gates. Okay, these transistors and logic gates, the logic gates is already studied in the digital electronics. Transistors, and we are going to study, or already some people are some students are studying in the analog electronics. There you will face the transistors, the BJT, FET, MOSFET, and this type of a transistor will work as the function of electronic switch. If switch means on or off, whether it has the on or off. The how we are going to represent in terms of the binary 0 and 1. 0 is related indicated to the off, and the 1 is indicated to the on. Okay, since the computers are work on the binary number system because it is on or off. Okay, and the important terms which are used in the computer literature is bit, nibble, byte, word, double word, and multiple word. Okay, one bit means one digit, one bit one digit. Okay, nibble 4 bits, 4 bits, or byte 8 bits, and the word 16 bits or the 2 bytes, double word 32 bits. These are the general terms used in the computer literatures to understand the bits and bytes. Okay, in the later system we will discuss that in the one digit in the binary, it has the 2 bits. If it is three digits, 2 digits or 3 digits in the octal system, the one digit is represented as 3 bits in the octal number system. In the one digit in the hexadecimal is represented the 4 bits. Okay, we can go up to the 4 into 4 16 in the hexadecimal, and the 3 into 3, it has the 9. Oh, 9. But it has the 8 bits to represent in the octal number systems. Okay, later slides I will show that how this number system is effectively changing depending upon their conversion tables. So here we are converting the one number system to other number system. Here I mapped the detailed procedure and the conversion between the one number system to other number systems is followed by the binary to decimal and decimal to binary, octal to binary, binary to octal, octal to decimal, and decimal to octal, binary to hexadecimal, hexadecimal to binary, hexadecimal to decimal, decimal to hexadecimal, hexadecimal to octal, hexadecimal to decimal. And here the conversion procedure for detailed conversion procedure. Here we can proceed further for integer part and fractional part, and we will solve the based on the integral part and fractional part. There the procedure will change for the integer part and the procedure change for the fractional part in the binary to decimal, decimal to binary, octal to binary, binary to octal, octal to decimal, decimal to octal, and followed by the binary to hexadecimal, hexadecimal to binary, hexadecimal to decimal, decimal to hexadecimal, hexadecimal to octal, and octal to hexadecimal. These are the procedure for the integer part and fractional part for the each and every conversion between the one number system to the other number systems. So these are the conversion table. You will see here octal we can represent up to 0 to 7, that is the 8 symbols 0, 1, 2, 3, 4, 5, 6, 7 up to the 7. Then it is represented 8 is equal to 2 to the power of 3 in the base 3 and the power is 3. Then how many digits are there? It is the power will represent the bits. Okay, in the octal system it has a 3 bits 0, 0, 0, and we are going to follow that the 8421 logic for the changing the numbers in the 1 2 4 8. 1 means only one bit change in the least significant bit, and the 8 means 8 bits are changed in the most significant bit. So, okay, later slides I will show that how the numbering will changing in the conversion table. For example, you will see here 16 is equal to the power of 4. Is the 4 is the bits, and the total in the hexadecimal how many is there? How many is there? There's the 16 means each bit, or we can say the digit. Okay, you can represent the digit here. We can see the digit starting from the 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Here the 3 digits 2 to the power of 4 in the 16 digit will come. But here in the hexadecimal each digit has the 4 bits, because hexadecimal number is representing into the 0 to 16. And the octal system it will represent the each digit has the 3 bits and it has the 4 bits. Okay, then it has a total number of 16 bits. It converting from the conversion table will go from the decimal to the binary and hexadecimal. So decimal number system is 0 to 15 is representing in the decimal number system, and the hexadecimal 0 to 9 is the numerical values, and A to F is the alphabetic value. So hexadecimal is the alphanumeric value system, and the decimal we are representing in terms of the hexa 1, 0, 11, 12, 13 up to the 31 location will represent as the 1F. Okay, 0001 to FFF. After that, we are going to change the locations in terms of the hexadecimal or decimal is the 31. Then you see here from the decimal number system 47, how we are going to represent in the 8-bit binary, that is 2F. 2F 00102 11111. This type, the each and every decimal number, the hexadecimal number is represented in the 2F. Next we will go for the 256 locations or 256 bytes. Later in the memory locations or memory addressing, I will teach, means I will use only the bytes. Is the 256 bytes or 4096 bytes or 4095 bytes or 4096 bytes. So here 2 to the power of 16 power of 2 is equal to 256. That is hexadecimal value. It represents in the 100. In the memory location, when we are going to change that, the each and every procedure, how the number system are changing in the 16-bit binary. So 0 to FFF, from the starting from 4 zeros to 0 FFF, it is total represent the 4096 locations in terms of the bytes. And here we will take the example 1. the different example we'll consider for the each and every conversion from the one number system to other number system, that is binary to decimal conversion. The example is that convert the 10101 is the binary number system to the decimal number system. So if the binary to decimal is the conversion from the binary to decimal is there, go and apply the positional weights. Okay, so 10101, they go for the positional weight in the hexadecimal binary number system, 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, and sum of this will represent it in the decimal number system. Okay, the 10101 is equal to the 21. If the decimal system it doesn't have the conversion table, if the decimal system will have the conversion table, then we can easily map this into 3 or 4 bits and represent into the hexadecimal or octal number systems. The later I will discuss that one. And what is the significant here? The two important points: least significant bit and the most significant bit plays a crucial role in binary number system representation. The MSB is the leftmost bit in a binary number system and carries the highest positional weight. You can see here the 10101 in the this one is the most significant bit, MSB, and it has the highest positional value, that is 2 to the power of 4, and LSB has the least positional weights. The LSB is the rightmost bit in a binary number system and carries the smallest positional value. And the same thing convert from the binary to decimal. Here the only the integer part is there. Here we are considering the fractional part also. So 11011 dot 101, this is the fractional part, 101 is the fractional part. For this, for the integer part you follow the positional weights, and for the integer part you'll go from the negative side, that is 2 to the power of -1, 2 to the power of -2, 2 to the power of -3, and sum all the values, then you will get the equivalent decimal value for the binary system. And here decimal to binary conversion, if the 52 is the decimal value, I will going to change in the binary. Then how we are going to change? Just divide the 52 value in terms of with 2, and the, whatever the remainder is there you can collect. So 52 divided by 2, 62, 26, you'll exactly 0, 0, 1, 0, 1, 1. Then follow from the bottom to top and take the 1, 1, 0, 1, 0, 0. It is the equivalent of binary of 52 in the decimal. Like that, each and every system I have explained here is the decimal to binary conversion, and the octal to binary conversion, and binary to octal conversion, octal to decimal conversion. See, here octal to binary conversion is very easy because octal system has the conversion table and the binary system has the conversion table. So you can see here the conversion table. Okay, my binary is the 3 bits. We have the representation of 0 to 7, and the 8 is equal to 2 to the power of 3. If 0 is equal 0, 0, 1 is equal 0, 0, 1, 2 is equal 0, 1, 0, 3 is equal 0, 1, 1, 4 is equal 1, 0, 0, like that. If I map this one, the octal number system is there. So octal and the grouping into the bits, the 3 bits, and mapping into the conversion table. So here, starting from the left side, you'll map here 2, 5, 7, 6, and 3. 3 means 0, 1, 1. Like that, it is the equivalent of octal value to the binary. Like that, here also binary to octal conversion. So from here, for the fractional part, we go from the left to right, and the integer part from the left to right, and chunk from the 3 bits, because octal system has the 3 bits. Okay, 101, 101 and 110. It is equivalent to 5, it is equivalent to 6, it is equivalent from the 10101. If any zeros are missed here, you consider the 0. Then this is the binary equivalent of the octal from the conversion table. But here, how we are going to map with the octal to decimal number system, because the decimal number system doesn't have the conversion table. Then you'll go for the positional weights or division. So here, octal to decimal, we are converting the octal number system to the decimal number system. We'll go for the positional value. If it is decimal to octal system, we'll go for the division values. Like that has followed in the first procedure, that is binary to decimal and decimal to binary. So here, decimal to octal number system will go for the division. Then again we have the two concept here. One is the integer value and another is the fractional value. So fractional value we multiply with the 8 octal system. and go for the up to 1 is occurred and take the value from the top to bottom, and for the integer part you take the bottom to top. Then these are the hexadecimal, these are the decimal value is equivalent to the octal conversion system. And you will see here the binary to hexadecimal conversion and hexadecimal to binary conversion, hexadecimal to octal conversion, and octal to hexadecimal conversion is very easy because the octal number system, binary number system, and hexadecimal number system have the conversion table. So you can see here the binary to hexadecimal. In the hexadecimal, how many bits are there? 3 bits are, 4 bits are there. So whatever the value is given in the binary, it just follow the procedure that from the integer part and the fractional part. For the integer part, you start from the right to left, and for the fractional part, you start from the right to left and chunks or group the 4 bits. Here 4 bits we are mapping. Then here the each hexadecimal digit has the 4 bits, that is 7C to FB from the conversion table. And the hexadecimal to binary also it is very easy because the each value has each digit has the 4 bits in the conversion table. But you will face the main problem here to hexadecimal to decimal conversion system, because hexadecimal has the conversion table but decimal number system doesn't have the any conversion table. Then you follow the positional weights and division rule. Okay, if it is converted from the conversion table now to the decimal number system, the decimal number system doesn't have the conversion table, then you go for the positional weight system. If you come from the decimal to hexadecimal, you go for the division, like that again for the two integer part and the fractional part. So here I want to convey that this it is the very important to indicate how the values are changing from the bits. Okay, here the 0 to f value is there. If I go for the, if I add the 1 here, okay, the addition, multiplication, subtraction and division will play the major roles in the locating the memory size. Okay, if I have the 1 KB of memory or 2 KB of memory, 1 MB of memory, 2 KB of memory, that memory size in terms of the bytes, I have to indicate in terms of the hexadecimal values. That is starting from the, if octal number system is 00302 FFF. If the hexadecimal number system is 4002 FFF up to the infinity of F, you can represent in the location of the address in terms of the bytes. So here the hexadecimal to octal conversion, and these are the special case. When the special case will come, will the value is very high, means 4 digit value in the hexadecimal in the decimal system will convert into the binary. So then if you go divide the 54972 by the 2222 with the two values, then it will take the whole page and it will take the whole page and you will not get the any answer. So here the better to go for the nearer conversion table system, that is octal. So binary it has the nearer conversion table system is the octal. So divide the 5497 in with 8, what are the value is coming in the octal system, then convert into the binary by grouping up the values of 3 bits. Then it is very easy. If it is, the binary number system is very high, the binary digits are given in very high. To again go for the positional weights, it will take half of the page to calculate the with the positional weight, starting from the 2 to the power of 0, 2 to the power of 1, 2 to the power of 2 up to n number of bits here. So I will do here first, I will convert to the nearest conversion table system, that is octal number system. For the, if this is not less than the 12 to 15, then I will go with the octal number system. If it is more than 15 to 20 digits, then I will go for the hexadecimal values. Okay, hexadecimal system, it is very convenient. It is for the just understanding purpose. Here I can go for the hexadecimal value also, here also I can go for the hexadecimal value also, but in the most of the computers we will use the hexadecimal values to calculate the positional and fractional weights. These are the same here, the you can see here the in the hexadecimal the 5 values are given. Then I will go for the hexadecimal value. Here the values are given very in terms of the binary it is more, if more bits are given, then I will go for the hexadecimal value for the calculating the position, because grouping up the 4 bits is very easy instead of 3 bits. If 3 bits means it will take the some time. Then it will I will group up with the 4 digits. Then it is very easily to calculate. So these are the some example problems I have solved and I gave the answer here. And anybody interested the watching in the YouTube, they are just to perform the values from the decimal to binary and check the answer exactly they are getting or not. Okay, here you will face the problem in when binary to decimal, decimal to binary, octal to decimal, decimal to octal, and hexadecimal to decimal and decimal to octal system. This 4 or 5 conversion only you will face the problem. Other than that, all the other three systems has a conversion table. If you go for the binary to octal conversion table, and the octal to binary or binary to hexadecimal or hexadecimal to binary or octal to hexadecimal, hexadecimal to binary, they have the conversion table. You can go from the follow the just procedure and map with the conversion table, you will get the answer. Okay, the three number system doesn't create the any problem, but in the hexadecimal to the decimal number system or decimal to the hexadecimal vice versa, we will calculate. Then you will face the problem whether how to go for the positional weight calculations or how to go for the division. Okay, if the simplest way to represent is the, if any conversion table, the system has the conversion table in your left side in the most significant side, that is MSB, representing in the left side. If is the conversion table is the hexadecimal to the decimal, in the right side LSB it doesn't have the decimal table, you go for the positional weights. Okay, that hexadecimal to decimal positional weight. Again you will see that the decimal to the hexadecimal. Okay, right side is the hexadecimal, it has the conversion table, and the MSB side it doesn't have the conversion table, that is decimal system. Then you go for the division. Okay, this is the simplest way of representing remembering the which system you have to follow the positional weights and the division rule for the decimal to hexadecimal or hexadecimal to decimal.